Let us discuss the chapter magnetism and matter. You can see in this diagram it is given the representation of the field lines. First one is of a paramagnet, bar magnet, second one is a current carrying finite solenoid, and third one is a electric dipole. Here you can see the difference in the magnetic field line of a bar magnet and current carrying finite solenoid is the same, but in case of electric dipole it is different. That is, they don't, they end at infinity. They don't have a particular point to end. Okay, next one. You can see this is a current carrying solenoid, so calculation, that is A, this one. Actual field of the finite solenoid in the order demonstrates its similarity to a bar magnet. And next one is a magnetic needle in uniform field B, and the arrangement may be used to determine either B or magnetic momentum of the needle. And here what you need to know is that in the bar magnet and equivalent solenoid concept, recall that the magnetic dipole moment M associated with current carrying loop was defined to be M equal to NAI, where N is the number of turns in the loop, I is the current, and A is the area vector. This is the formula which you need to remember. And the next formula which you need to remember is, see, this chapter is fully formula based and a bit of concepts. B equal to mu naught divided by 4 pi into 2m divided by r cube. And next is dipole in uniform magnetic field, tau equal to m into b. And the next formula is, you did not learn this, just the main part of the formula is required, that is b equal to 4 pi square I divided by mt square, and um equal to minus m into b. And see, that is all the first question. In figure B, some figure, the magnetic needle, that figure which I showed, needle has magnetic moment 6.7 in 10 to the power minus 2 area per meter square, and the moment of inertia is this, and it performs 10 complete oscillation in 6.70 seconds. What is the magnitude of magnetic field? See, first of all you need to find the magnitude of magnetic field. That this is the formula for that. You need to see 4 pi I is given, m is given, magnetic moment, and t is not given, so we need to find t, that is this one, seconds of oscillation divided by the number of oscillation, that is 10 complete oscillation, gives this, and when you substitute you get the answer. Let's move to the next question. Okay, next question is a short bar magnet placed with axis at 30 degree with the external field at 800 G experiences a torque of 0.016 Newton meter. A, what is the magnetic moment of the magnet, and B, what is the work done in moving it from its most stable position to unstable position. And C, the bar magnet is replaced by a solenoid of cross section area this and 1000 turns, but the same magnetic moment of the same. Determine the current flowing to the solenoid. So the solution is, see, from that equation you know that tau equal to mb sin theta, and you have to consider sin theta for some case and cos theta for some other case, and you see theta equal to 30 degree which is given in the question, and hence sin theta is 1 by 2, sin 30 is 1 by 2, and you substitute and get the answer of m. You know what is tau, and you also know what is b, and you need to find m. Now from again another equation, what happens is that equation, that is this one, u equal to minus m into b. The most stable position is theta equal to 0 degree, and the most unstable position is theta equal to 180 degree. Then the work done is stable minus, of course it is unstable minus stable, that is theta equal to 180 degree minus equal to 0 degree. So minus and minus becomes plus, it becomes 2 mb, and is the answer. Then from equation 4. The one which I showed you in the starting, that is ms equal to INA. From part A, ms equal to this, from first part, that is A, you found the value of m and just substitute over there, and you find the value of I, and you get the answer. Determine the current flowing to the solenoid. Okay, let's go to the next question. What happens if a bar magnet is cut in two pieces? One is transverse to its length and another is longitude along its length. In either case, one gets two magnets each with north and south pole. A magnetized needle in uniform magnetic field experiences torque but no net force. A iron nail near the bar magnet, however, experiences force of attraction in addition to the torque. See, No force in the field is uniform. The iron nail experiences a non-uniform field due to the bar magnet. This is induced magnetic moment in the nail. Therefore, it experiences both force and torque. The net force is attractive because the induced south pole, just consider south pole, in the nail is closer to the north pole of the magnet than the induced north pole. Okay, must every magnetic configuration have a north pole and a south pole? Then what about the field due to a toroid? In toroid is different field. No, it's not necessary. True only if the source of the field has net non-zero magnetic moment. This is not so for toroid or even for a straight infinite conductor. Now, two identical looking iron bars A and B are given, one of which is definitely known to be magnetized. That is, we do not know which one. How would one ascertain whether or not both are magnetized? If one is magnetized, how does one ascertain which one? So try to bring different ends of the bar closer. The repulsive force in some situation is established that both are magnetized. If always some situation they are attractive of, and then one of them is not magnetized. If the bar magnet, the intensity of the magnetic field is the strongest at two ends of the pole and the weakest at the central region. This fact might be used to determine whether A and B magnet, A or B is a magnet. In this case too, we see that one end of the two magnet is bars is a magnet. Pick one, say, and lower one its end. First one in one end and say B in other end, and then one middle B. If you notice that in the middle of B, A experiences no force, then B is magnetized. If you do not notice any change from the end to the middle of B, then A is magnetized. Next topic, that is electrostatic analogy. In this you just need to know this two formula, that is B, which is equatorial field, equal to minus mu naught m divided by 4 pi r cube, and BA, that is axial field, equal to mu naught divided by 4 pi into 2m divided by r cube. Okay, now let's come to this problem. What is the magnitude of equatorial and axial field due to a bar magnet of length 5 cm at a distance of 50 cm from its midpoint? The magnetic moment of bar magnet is 0.40 A, that is ampere meter square, and the same as in example 5.2. You have to consider the same example that we dealt in 5.2. Let's see 5.2. You can see over here the cross section is the same value of 1000 turns and that. Okay, now the solution from equation 5.7. See 5.7, this equation. According to this equation, you just have to substitute mu naught is given, that is 10 raised to the power minus 7. Okay, figure. Now if you consider this question in the figure 5.5 shows a small magnetized needle P placed at a point O, and the arrow shows the direction of its magnetic moment, and the other arrow shows different position and orientation of the magnetic moment of another identical magnetized needle Q. A, in which configuration of the system is not in equilibrium, which configuration the system is not in equilibrium, and B, in which configuration is the system, one is stable, B is unstable equilibrium, and in which configuration the corresponds to lowest potential energy among all the configurations shown. The solution: potential energy of the configuration arises due to potential energy of one dipole, that is say Q, in the magnetic field due to other P. Use the result that the field due to P is given by the expression in those equations 1 and 2, that is BP, and just consider the point P, that is equal to minus mu naught MP divided by 4 pi into R cube on the normal bisector, and BP equal to mu naught 2 MP divided by 4 pi into R cube on the axis, where MP is the magnetic moment of the dipole P. Equilibrium is stable when MQ is parallel to BP and unstable when it is anti-parallel to BP. For instance, for the configuration Q3, for which Q is along the perpendicular bisector of the dipole P, the magnetic moment of Q is parallel to the magnetic moment of position 3, and hence Q3 is stable. Thus, in the first one, in which the configuration the system is not in equilibrium, that is PQ1 and PQ2, and in which configuration the system is in one is stable and two is unstable equilibrium. In stable equilibrium Q3 and Q6, and in unstable equilibrium Q5 and Q4, and in which configuration corresponds to the lowest potential energy potential energy among all the configurations shown, that is PQ6. Okay, you just need to remember the formula for Gauss law of magnetism, that is this called psi b equal to psi of phi b equal to summation of all delta phi b equal to summation of all b into s delta s equal to 0, and where all stands for all area elements ds. Compare with the Gauss law of electrostatic, the flux to the closed surface in this case given by summation of summation of E into delta s equal to q divided by epsilon naught. Now the Gauss law for magnetism is the net magnetic flux to any closed surface is 0. Now let us solve an example. Many of the diagram are given in figure this one 5.7 and shows the magnetic field lines, that is thick lines in the figure. Wrongly point out the wrongly pointed one with them. Some of one may be describe electric field lines correctly. Point out which one. See, in this diagram you can see some are wrongly represented and some are correctly represented. Let us come to this figure A. Do you think it is correct? I don't think so. It's wrong. The magnetic field lines can never emanate from a point as shown in the figure. See, it can never come from a point like this. That is wrong. And over any closed surface, the net flux B must always be 0. That is, pictorially, as many field lines should be seen to enter the surface as number of lines leave it. And if field lines shown in fact represent electric field line as long positively charged wire, and correct magnetic field lines are circled in straight conductor as described in chapter 4. And next one, yes, of course, it's represented correctly. Let us see. Okay, it is represented wrong. Hey, see, I told it's correct. But why do you think it's wrong? Oh, because it is not B, it is E. Okay, this is correct. Now this B is wrong. Okay, this is E and this is B. Okay, this is wrong in empty space. And you can see E is right. Okay, B it's wrong. Why? Why is it wrong? Magnetic field lines like electric field line can never crisscross each other, because otherwise the direction of field at a point of intersection is ambiguous. There is further error in the figure. Magnetostatic field lines can never form closed loop around empty space. A closed loop of static magnetic field line must enclose a region across which a current is passing. By contrast, electrostatic field lines can never form closed loop, neither in empty spaces nor when the loop encloses charges. Okay, you already saw the answer of the next question, and it is this C. Do you think it's correct? Of course, you saw the answer. It's right. C. It's a toroid. Okay, magnetic lines are completely confined within a toroid. Nothing wrong here in the field lines forming closed loop, since each loop enclosed a region across a current passes. Note that the clarity of figure only in few field lines within the toroid have been shown. Actually, the entire region enclosed by the winding contains magnetic field lines. Okay, next one. Do you think this is correct? This is wrong. Why? Because the field line due to a solenoid at the ends and outside cannot be so completely straight and conformed. Such a thing violates Ampere's law. It cannot be so straight. The line should be curved at both the ends and meet eventually to form the right kind of loop. So the next question, which I already told the answer, it's correct, E. So these field lines cannot possibly represent a magnetic field. Look at the upper region. At the field lines seem to emanate out of the shaded plate. The net flux to a surface surrounding the shaded plate is not 0. This is impossible for magnetic field. The given field in fact shows the electrostatic field lines around a positively charged upper plate and negatively charged lower plate. The difference between this the figure should carefully be grasped. Okay, I hope you understood this. And let's see, G, is it correct or wrong? Okay, let us see what. It is wrong. Let's see why. Magnetic field lines between two poles, that is two pole pieces, cannot be precisely straight at the end. Some fringing line is inevitable, otherwise Ampere's law is violated. It is also true for electric field lines. Yes. And the next example, last example. Study the topic Earth's magnetism. See, what causes Earth to have a magnetic field is not clear. Originally, the magnetic field was thought to arise from a giant bar magnet placed approximately along the axis of rotation of the Earth and deep in the interior. However, this simplistic picture is certainly not correct. The magnetic field is now thought to arise due to electrical current produced by convective motion of metallic fluid consisting mostly of molten iron and nickel. In the outer core of the Earth, it is known as Dynamo Effect. And here you can see the Earth is a giant magnetic monopole, and these points are not included. Cut it. This is the magnetic equator, and this is geographic equator. And the convention arose because the magnetic north was direction to which the north pole of the magnetic needle pointed, and the north pole of the magnet was so named as it was north seeking pole. Thus in reality north magnetic pole behaves like south pole of a bar magnet inside the earth and vice versa. Let us try this problem. The Earth's magnetic field at the equator is approximately 0.4 G. Estimate the Earth's magnetic dipole. From equation, the equatorial magnetic field is this, and we are given that B equal to this G, and when we convert it into Tesla, this is the value. For R, we take the radius of the Earth as this, and M find the value. This is the answer. Now let us study about magnetic declination and dip. See, this is the magnetic needle free to move in horizontal plane points towards the magnetic north and south direction. Consider a point on the Earth's surface. At such point, the direction of the longitude circle determines the geographic north-south direction, and the line of the longitude towards the North Pole being the direction of the true north, and the vertical plane containing the longitude circle and the axis of rotation of Earth, and is called geographic meridian. In similar way, one can define magnetic meridian of a place as the vertical plane which passes through the imaginary line joining the magnetic north and south pole. This plane would intersect the surface of the Earth in a longitude-like circle. A magnet needle which is free to swing horizontally would then lie in the magnetic meridian, and the north pole of the needle would point towards the magnetic north pole. Since the line joining the magnetic pole is tilted with respect to geographic axis of the Earth, the magnetic meridian at a point makes an angle with the geographic meridian. This then is the angle between the two geographic north and the north shown by the compass needle, and this angle is called the magnetic declination or simply declination. The declination is greater at altitude and smaller near the equator, and the declination in India is smaller, and it being this degree at Delhi and this at Mumbai. Thus both the places have magnetic needles showing the two not quite accurately. This is one more quantity of interest. If the magnetic needle is perfectly balanced about the horizontal axis, so it can swing in a plane of the magnetic meridian, the needle would make an angle with the horizontal and is known as angle of dip, also known as inclination. Thus dip is the angle that the total magnetic field B of the Earth makes with the surface of the Earth. And this figure shows the magnetic meridian plane at a point P on the surface of the Earth, and the plane is a section through the Earth, and the total magnetic field at P can be resolved into horizontal component HE and vertical component ZD, and the angle B makes with HE is the angle of dip I. And you see in this circle, the circle is a section through the Earth, a section of the Earth containing the magnetic meridian, and the angle between B and the horizontal component HE is called as the angle of dip. You can see in this. And here the Earth's magnetic field B is the horizontal and vertical component, and HE and ZD also shown are the declination D and inclination or angle of dip I. And these are its formula. What you need to know is that ZE equal to B sin I, HE equal to B cos I, which gives tan I equal to ZD divided by HE. Now let us try this problem. In the magnetic meridian of certain place, the horizontal component of Earth's magnetic field is 0.26 G and the dip angle is 60 degree. What is the magnetic field of the Earth at this location? It is given that H equal to this, and from the figure 5.11, that is this figure, as I told, cos theta equal to H divided by B, that's cos 60 degree. From the figure is BE equal to H divided by cos 60 degree, and you get the answer. Now let us go move to discuss some formula that is B naught equal to mu naught Ni. So what is B? B is the field, as you know, and mu naught is, you know, the susceptibility N and I, you know, I is the current, and B equal to B naught and Bm. You know, B is the field contributed by the material core, and additional field Bm is proportional to magnetization. No, just leave that. You know, B naught and Bm. B0 is just the constant of that, and Bm is the magnetic field, and Bm equal to mu naught M. And you see, mu naught is the same constant that is permeability of the vacuum. M is the magnetization, and you know, H is next term which comes is H, that is magnetic intensity here. H equal to B divided by mu naught minus M, and B equal to mu naught of H plus M, and M equal to X or psi or chi into H, where chi is the somewhere over here, yeah, is a dimensionless quantity and is called magnetic susceptibility. Here B equal to mu naught 1 plus chi into H equal to mu naught mu r H equal to mu H, and is relative, you know, mu r equal to 1 plus chi, that is, it's a dimensional quantity called relative magnetic permeability of a substance, and is analog of dielectric constant in electrostatic. And the magnetic permeability of substance is mu, and it has the same dimension, and unit is mu naught, and mu equal to mu naught r equal to mu naught 1 plus chi, and its three quantities chi, mu r and mu r interrelated, and only one of them is independent. Given one, the other two may be determined. Okay, let us solve this example. What it tells is that a solenoid has a core of a material with relative permeability 400, and the windings of a solenoid are insulated from the core and carry a current of 2 ampere. If the number of turns are 1000 per meter, calculate H, M, B and magnetization current I. So first let us calculate H. H, you know the formula, that is field H is dependent on the metal of the core and is H equal to Ni. The formula is not given, but you just need to remember H equal to Ni, that's 1000 into 2.0 gives this, and the magnetic field B is given by B equal to mu naught mu r mu naught into H, answer. And magnetization M is given by B minus mu naught H divided by mu naught, that you can derive from this formula over here. Or even you can derive this directly from this. And next is the magnetization is given by that, and the answer. And you know, D, what you need to find the magnetization current. The magnetizing current IM is the additional current that needs to be passed through the windings of the solenoid, here to be passed to the winding of the solenoid in the absence of the core, which would give a B value as in the presence of the core, and the B equal to mu naught R N naught I of I plus M. Using these values we get this. Now let's go to the next topic, magnetic properties of material. See, here you need to remember this table, which is very important, that is diamagnetic, the chi comes in between -1 to 0, and it is also equal to -1. For paramagnetic, chi comes between 0 and epsilon, and in ferromagnetism chi is very greater than 1, is much greater than 1, and here mu r comes between 0 and 1 and is also equal to 0, and here you know mu r comes between 1 and 1 plus epsilon, and mu r is much greater than 1 in case of ferromagnetism. Here diamagnetism mu is less than mu naught, and paramagnetism mu is greater than mu naught, and in ferromagnetism mu is much greater than mu naught. So in figure you can see the behavior of magnetic field lines near this is diamagnetic, and near paramagnetic substance you can see the behavior. And see, let us read about diamagnetism. The most exotic diamagnetic material are superconductors, and these are metals cooled to very low temperature which exhibit both perfect conductivity and perfect diamagnetism. Here the field lines are completely expelled, that is chi is equal to -1 and chi equal to 0. A superconductor repels a magnet, and by Newton's third law is repelled by the magnet, and the phenomenon of perfect diamagnetism in superconductor is called the Mesonos Effect, and after the name of its discoverer. Superconducting metals can be gainfully exploited in variety of situations, and for example for running magnetically leviated superfast train. Now let us discuss about paramagnetism. See, in the presence of an external field B naught which is strong enough, and at low temperature the individual atomic dipole moment can be made to align and point in the same direction as B naught. And this formula, that is m equal to c B naught divided by T, and chi equal to c mu naught divided by T. And let's read about ferromagnetism. See, first of all, before that you need to know, this is a kind of ferromagnetism. Here first one is oriented domains and second one is aligned domain. Just remember that. See, in ferromagnetism what happens is that in a ferromagnetic material the field lines are highly concentrated, and in non-uniform magnetic field the sample tends to move towards the region of high field. We may wonder as to what would happen when the external field is removed. In some ferromagnetic material the magnetization persists. Such materials are called hard magnetic material or hard ferromagnet. Al, aluminium, alnico, it's an alnico. Alnico, an alloy of iron, aluminium, nickel, cobalt and copper, is one such material. It is naturally occurring lodestone is another. Such metal form permanent magnet to be used among the things as compass needle. On the other hand, there is a class of ferromagnetic material in which the magnetization disappears on removal of external field. Soft iron is one such material. Appropriately enough, such material are called soft ferromagnetic material. Now there are a number of elements which are ferromagnetic. Example: iron, cobalt, nickel, gadolinium, etc. The relative magnetic permeability is greater than 1000. The ferromagnetic property depends on temperature. At high enough temperature, a ferromagnetic magnet becomes a paramagnet, and the dominant structure disintegrates with temperature, and this disappearance of magnetization with temperature is gradual. It is a phase transition, reminding us of the melting of solid crystal. The temperature of transition from ferromagnetic to paramagnetic is called Curie temperature, Tc. The table lists the Curie temperature of certain ferromagnetic, which is not at all important, don't read it. And if susceptibility above the Curie temperature, that is in the paramagnetic phase, is described by chi equal to c divided by c minus c Tc at Curie temperature Tc, that is T is greater than Tc. So let us solve this example, that is 5.11. A domain in ferromagnetic iron is in the form of a cube of side length 1 micrometer. Estimate the number of iron atoms in the domain and maximum possible dipole moment and magnetization of the domain. The molecular mass of iron is 55 gram per mole and its density is 7.9 gram per centimeter cube. Assume that each iron atom has a dipole moment of 9.27 in 10 to the power minus 24 area per meter square. Let's solve. Okay, now the solution. The volume of the cube domain is V equal to this. You find its mass is volume into density. You find, and it's given that Avogadro number of the iron have mass of 55 gram. Hence the number of atom in the domain is N equal to. You need to use the formula of N. Just see the values which is given. Okay, here N is this is the value of mass, volume and density, and this Avogadro number, and this is the molecular mass. Obviously you can see the molecular mass of iron is given in the question, and the maximum possible dipole moment Mmax is achieved for unrealistic case when all the atomic moments are perfectly aligned. Thus Mmax equal to this one N into dipole moment, and the value of dipole moment is given over here. Dipole moment of so much mass in dipole moment comes the answer. The consequent magnetization is Mmax equal to Mmax divided by domain value, and the domain volume, Mmax is this divided by domain volume, and 8 10 raised to the power minus 18 is given somewhere over here. 10 raised to the power, this is the domain volume, and you get the answer. Okay, let's come to the next topic, that is the magnetic hysteresis loop for the BH curve for ferromagnetic material. We'll explain this. See, we decrease H and reduce it to 0. Then what happens is that H equals 0 and B is not equal to 0. This represented by a curve AB, and the value of B at H equal to 0 is called retentivity or remanence. At H equal to B is called retentivity or remanence, And in this figure, Br is almost 1.2 Tesla, where the subscript R donates retentivity, and the domains are not completely randomized, even though the external driving force field has been removed. Next, the current in the solenoid is reversed and slowly increased. Certain domains are flipped until the net field inside strand nullified, and this is represented by the curve Bc, and the value of H and C is called coercivity. In this figure, H is almost equal to minus 90 ampere per meter. So almost equal to minus 90 ampere per meter. It's not given, yeah, minus 90 ampere per meter. And as the reverse current is increased in the magnitude, and once again we obtain the saturation, the curve CD depicts this one, and the saturated magnetic field Bs, it's almost 1.5 Tesla. Next, the current is reduced to curve D and reversed to curve C, and the cycle repeats itself. Note that the curve OA does not retrace itself as H is reduced, and for the given value of H, B is not unique but depends on the previous history of the sample. The phenomenon is called hysteresis, and the word hysteresis means lagging behind and is not history. Now let's go to the next page. No important concept, and the chapter comes to an end. Okay, now let us read some crucial summary that when a bar magnet of dipole moment M is placed in uniform magnetic field B, the A force on it is 0, the torque on it is M into B, and its potential energy is minus M into B, where we choose the 0 of energy at orientation when M is perpendicular to B. Consider a bar magnet of size L and magnetic moment M at a distance R from its midpoint, where R is much greater than L, and the magnetic field B due to this power magnet is B equal to mu naught M divided by 2 pi R square, which is equal to minus mu naught M divided by 4 pi R cube, not square cube. This along the axis and along the equator. Gauss law for magnetization states that the net magnetic flux to any closed surface is 0. That is phi B equal to summation of all area elements, or delta S B into delta S equal to 0. And next, nothing much important. Now points upon all is important, and see, a satisfactory understanding of magnetic phenomena in terms of moving charges current was arrived after 1800 AD, but technically exploitation of the directional properties of magnet predates the scientific understanding by 2000 years. This scientific understanding is not necessary condition for engineering application. Ideally, it is not necessary condition, and ideally engineering go hand in hand and one leading assists the other in tandem, and the magnetic monopoles do not exist. If you slice a magnet into half, you get two smaller magnets. On the other hand, isolated positive and negative charges exist. There exists a smaller unit of charge, for example the electronic charge, with value modulus of E equal to 1.6 in 10 to the power minus 19 coulomb, and all the charges are integral multiple of the smallest unit charge. In other words, charge is quantized. We do not know why magnetic monopoles do not exist or why electric charge is quantized. Now the third point is consequence of fact that magnetic monopoles do not exist. The magnetic field lines are continuous and form closed loop. In contrast, the electrostatic lines of force begin on a positively charged and terminate on a negatively charged or fade out at infinity. Fourth point is that the Earth's magnetic field is not due to a huge power magnet inside it, and the Earth's core is hot and molten. Perhaps convective current in this core are responsible for Earth's magnetic field. As to why what Dynamo Effect sustains this current, and why the Earth's field reverses polarity every million years or so, we do not know. A minuscule difference in the value of chi, the magnetic susceptibility, yields radically different behavior, diamagnetic versus paramagnetic. For diamagnetic material, chi equal to minus 10 raised to the power 5, whereas chi is plus 10 raised to the power minus 5 for paramagnetic material. There exists a perfect diamagnet, namely a superconductor. This one is a metal at very low temperature. In this case, chi is minus 1 and mu r equals 0, and the external magnetic field is totally expelled. Interestingly, this material is also perfect conductor. However, there exists no classical theory for which ties these two properties together. A quantum mechanical theory by Barden, Cooper and Scriffel, that is Bcs theory, explains this effect. And the Bcs theory was proposed in 1957 and was eventually recognized by a Nobel Prize in physics in 1970. The seventh point is that the phenomenon of magnetic hysteresis is Remnant of similar behavior concerning the elastic property of material. Strain may not be proportional to stress. Here H and B or M are not linearly related. Stress strain curve exhibits hysteresis and area enclosed by it represents the energy dissipated per volume. A similar interpretation can be given to the BH magnetic hysteresis curve. Its point is that the diamagnetism is universal. It is present in all material, but it is weak and hard to detect if the substance is para or ferromagnetic. 9th point is that we have classified materials as diamagnetic, paramagnetic and ferromagnetic. However, there exists additional type of magnetic materials such as ferrimagnetic, antiferromagnetic, spin glass, etc. With properties which are exotic and mysterious. Thank you. You guys, you need to solve question to improve your concepts. All good level questions. Pretty decent ones. Especially section B, which is my favorite. Yeah. And yeah, your chapter comes to an end. Thank you. These are the answers for magnetism and matter. Thank you. Have a nice day. Bye. Okay guys, if you like my video, do hit the bell icon and subscribe button so that you will be notified with all upcoming videos, which is fully free, and enjoy unlimited lectures. Thank you.